Hello everyone, today I'll be discussing bleach decomposition. First, introduction. Sodium hypocrit, commonly called bleach, acts as a disinfectant, a cleaner, also a bleaching agent, widely used. It is important for wool sanitation since it kills fungi, viruses, bacteria. However, its reactions with organic matter as well as decomposition create concerns with regard to NaOCl decomposition, plus show the reasons why conditions like heat, light, and pH matter here. I will outline health and environmental impacts, also connect the issue to equity and climate, and propose practical solutions. Explain the chemistry, part 1. Word equation. Sodium hypochrate equals to sodium chloride plus oxygen. The formula equation. NaOCl equals to NaCl plus O2. The balanced equation. NaOCl equals to 2 NaCl plus O2. Reaction classification. Decomposition. One compound equals simple products and redox. In NaOCl, oxidation states Na plus O2 minus Cl plus 1. In NaCl, Cl is minus 1. In O2, oxygen is 0. So chlorine is reduced. Plus 1 equals negative 1. And oxygen is oxidized. Negative 2, 0. Half reactions, iconic view. Oxidation, oxygen, 2O2 minus equals O2 plus 4E minus. Reduction, chlorine, 2Cl plus 1 plus 4E minus equals 2Cl minus. Combine, 2 NaOCl equals to 2 NaCl plus O2. Electrons cancel. Key points. Mass and atoms are conserved. Sodium chloride and oxygen atoms are present before and after the reduction, even if the forms change. Now we go for explain the chemistry part 2. Conditions that changes the pathway. Heat raises reaction rates. Bleach stored warm decomposes faster, releasing O2 and producing chlorine containing species. Light photo decomposition accelerates breakdown. Opaque bottles slow this. pH acidity critical. Under acidic conditions, NaOCl can produce chlorine gas CO2, which is highly toxic. Explain reaction with acid. NaOCl plus 2HCl equals to NaCl plus Cl2 plus H2O. Mixing with ammonia or organic N compounds produces chloramines, NH2Cl, NHCl2, and NCl3. Respiratory irritants. Reaction with organic matter yields chlorinated organic byproducts. Example. Oh yeah, and then yeah. So what I'm talking about, mixing with ammonia or organic N compound produces chloramines, which is again I just told, and then reaction with organic matter yields chlorinated organic byproducts. Example, THMS like chloroform and haloacetic acids. These are toxic and can be carcinogenic. And be yeah, carcinogenic. And then we have we have real world actions, which is bleach is a strong oxidizer. Contact can cause chemical burns, vapors, irritate the eyes, and respiratory tract. Repeated exposure may contribute to chronic lung conditions. Mixing bleach with acids, including vinegar or ammonia, produce have can produce chlorine gas or chloramines. Both can cause acute respiratory injury and have led to evacuations and fatalities in industrial and household incidents. Example: chlorine gas releases have resulted in mass evacuations and hospitalizations. Poison control centers report thousands of bleach-related incidents annually. Misuse rose during COVID-19 due to increased household disinfection. Workers in manufacturing, storage, and wastewater plants face higher exposure risks without proper PPE, ventilation, and training. When NaOCl enters wastewater, it reacts with organic matter to create chlorinated organics, THMS, HAAS, chloroform. These can persist, are toxic to aquatic life, and some are carcinogenic to humans. Bleach can kill beneficial microbes in soil and aquatic systems that maintain nutrition cycle and waste breakdown, causing knock-on effects through food webs. Reduced oxygen availability, gill damage in fish. Long-term contamination can change soil chemistry and leach chlorinated compounds into groundwater, threatening drinking water sources. Now we have the equity and social justice. Equity. Industrial plants and waste sites are disproportionately sited near low. low income and marginalized communities, increasing local exposure to air and water contamination. Indigenous and rural communities dependent on surface waters are especially vulnerable. Regulatory enforcement and access to protected resources are often unequal. Climate links. Production. Electricity of brine consumes significant energy. If the electricity comes from fossil fuels, manufacturing adds CO2 emissions. Warming climates accelerate decomposition and storage instability. Higher temperatures equals faster breakdown. And extreme weather increases spill risk, spreading contamination. Some volatile chlorinated compounds also affect atmospheric chemistry, albeit at small scales relative to CO2 and methane. Now we have practical solutions. Now, personal and household. Use bleach only when necessary and follow label directions. Dilution, ventilation, PPE. Never mix bleach with acids, vinegar, ammonia, or household cleaners. Prefer alternatives for routine cleaning, hydrogen peroxide, or alcohol-based disinfectants when appropriate. Do not mix these with bleach. Avoid dumping large volumes of concreted bleach down drains. Dilute and follow municipal disposal guidance. Community/institutional. Improve labeling and public education about incompatible mixes and safe storage. Promote PPE and training for workers in manufacturing and sanitation sectors. Upgrade wastewater treatment to remove or neutralize chlorine residues and chlorinated byproducts. Decoloration, activated carbon, advanced oxidation where needed. Encourage hospitals and schools to pilot green disinfectants for routine use. Police/industry bay. Incensi- Incentivize renewable electricity for industrial sodium hypocrit production to reduce life cycle CO2. Enforce sitting and emission rules that protect vulnerable communities, improve monitoring and rapid response for spills. Set and enforce strict limits on THMS and related byproducts in drinking water. Many jurisdictions already do this. Continual review is important though. Now we have the short conclusion. Bleach is a powerful and useful disinfectant, but its chemistry has trade-offs. Decomposition and side reactions produce hazardous gases and persistent chlorinated compounds that harm health ecosystems and vulnerable communities. Understanding the redox chemistry and the role of temperature, light, and pH helps us prevent accidents. Combining informed personal behavior with wastewater controls, cleaner production, and equitable siting and regulation is the path to retaining bleach's benefits while reducing its harms. For this project, I used AI in a limited, intentional way, like a research assistant to find sources right over here. Again, like I said, I used AI in a limited, intentional way, like a research assistant to find sources on bleach and its environmental impacts. The real work of reading, evaluating, and rewriting was mine, though. This approach kept the project in my voice while letting AI speed up the research process. And some of my references are right over here. There's a lot of them. I'm gonna just read some of them for you. Bibliochong, Parveen, and American Cleaning Institute, and then New Jersey Department of Health. That's just some of them. And that's pretty much the end of my presentation. I also want to say that I rushed most of this because I didn't have enough time. When I first realized this, when my real project was 15 minutes long, but it was very detailed and it was very nice. But clearly, the requirement says to only do 7 minutes, so I couldn't do as much well as possible. So I had to kind of rush through this. And I'm sorry if you couldn't understand me because my audio is kind of bad and I may not sound as clearly as I speak right now. But I had to really rush most of it. So, yeah.